Hello and good morning, or good afternoon, or good evening, or whenever you're viewing this. The file we have here is for my Physical Sciences for Teachers lab. It might be more general, so I'm going to make this public, but it's a very specific thing made for one course, and I'm introducing a lab activity that's labeled plane mirrors in the lab manual. So it's about reflection and plane, that is flat, mirrors. While I am writing it for this specific course, the general content at the beginning is pretty much in every introductory physics class at some point, everywhere from high school physics up through the calculus-based physics that people take when they're going to be engineers or scientists. I actually wrote the slides for a different course originally, and I've adapted some of them with a little less vocabulary and math in them. The video I show at the end is very specific to this lab activity. Honestly, it's mostly there for a little bit of fun. The first point is to talk about reflection. And before I even show you any words here, I'm going to make a big point about some vocabulary. The person on the other side of the mirror that you see, we don't call that reflection in physics. We call that the image of you. Reflection is the phenomenon that occurs when light bounces off of the mirror, or when any wave bounces off of any surface. And if you first looked at reflection in lecture part of the course, talking about other kinds of waves, you might have considered wave fronts for waves that are more than one dimension. That is, if you think of water waves, the crests of the wave as they move along might bounce off of some surface at the end of an aquarium or something and go in a different direction. Now the blue arrows I've drawn here are the directions. The lines that are solid on the incoming ones, dashed on the outgoing ones, are the wave fronts at some particular moment. We're interested just in the directions, and we'll treat light as though it moves along in straight lines until it hits a surface and then may do something like reflect. To do that, we'll need to talk about a little bit of math and a little bit of vocabulary. Normal to the surface, normal is just a math word for perpendicular. It's an imaginary line perpendicular to the surface wherever I want to draw it. And I want to draw it where the incoming, or we say incident, ray hits the surface, which is also where the outgoing or reflected ray comes from the surface. The law of reflection, which people talk about in every book at this level or all of the levels I talked about, it has two parts, and we often only talk about one of them. The first part, the part we always talk about, is that the angle of incidence is equal to the angle of reflection, and those angles are measured from the normal to the reflecting surface. The second part, the books sometimes omit mentioning, is actually really important if you want to have a full treatment of this, but there's a good reason that a lot of books don't bother mentioning it. The part is that the reflected rays lie in the same plane with the incident ray and the normal to the surface. That is, you can draw it all on one flat piece of paper. In fact, if you have a book or a computer screen, you're drawing things on a 2D surface anyway, so everything is in a plane. That's not the real reason they probably don't bother mentioning it. So it sounds complicated, but really it's what most people would assume anyway. That said, again, if you were doing a very formal mathematical treatment, this would be critical. But for the pictures we're going to look at, it's not such a big deal. So I want to look at a mirror now. So I draw a mirror with an object in front of it. The mirror is this line, so I'm imagining that the mirror is not in the plane of this screen. It's coming out at me. And the object is this little dot over here. If I draw a ray of light from that dot to the mirror, and I follow the law of reflection, I draw my normal to the surface, I measure my angle of incidence, and my angle of reflection tells me the ray comes out this way. I can do that again, draw a second ray, and I can, because I choose to, trace back to see where these rays look like they come from. And of course the lines cross somewhere. Almost any two lines that you draw on a plane are going to cross somewhere. But the interesting point is that if I keep doing this, if I draw many lines, I find they all look like they came from the same place. And that's important. That's really the point here. All of these reflected rays appear to have come from one point behind the mirror. That point is, as you've guessed, the thing we call the image. Now, depending on the course you're in, and in fact for this course, probably in lecture you're going to go through and do some math with some triangles and base this on drawing another normal to the surface from the object through the surface, and you'll find that that passes through the image that you've just drawn. And you can do some geometry with triangles like the ones here and some other pieces, and you'll find that you can prove some things about where that image is. And many of these are things you know, but you never proved them with physics and geometry. So the things you prove are an image can be formed, that is, it will look like the light came from one place if it originally came from one place. And it's behind the mirror, in fact, by a particular distance, the same distance as the object is in front of it. And the object and the image lie on a single normal to the plane, which is kind of important actually, because that, along with the distance statements, implies that the size and shape of an image for something bigger than one point are not distorted, which is what you know. You look in the flat mirror when you get up and go into the bathroom in the morning and wash your face, and you see your face the same way it really looks, or at least the same way you think it looks. Now, you may have heard something when you were a kid from parents or teachers or anyone, maybe just figured it out yourself, about switching left and right. I claim that this image is upright, that is, your head is on the top, its head is on the top. But it's also not left-right switched. I'm not going to go into that a lot more now, but when I do the class, I actually demonstrate that, either with a real mirror or sometimes just pretending the board is a mirror. But you will need to keep that in mind when answering questions for this lab.
We're going to talk about images in a mirror, a plane mirror, a flat mirror that is. And since faces are pretty symmetric generally, I usually demo this with something other than a face. My wife's been after me to trim my mustache and shave for a while, so I thought halfway through might be a nice time to try this. And notice I've shaved the right side of my face and trimmed my mustache. And I'm going to look in the mirror, and my bathroom has a little side mirror as well. So here what I've got is myself in the mirror, myself in the mirror, and myself in the other mirror. We're going to talk about what those look like when we meet for lab today. I'm going to talk about what really goes on with a mirror, and what you think you see and what you heard as a kid you see may be a little different from what you're really seeing. See you in class. Bye.
That was really just kind of for fun, but part of what's in the lab activity is to look in a pair of mirrors that are at right angles to each other, and I happen to have had that set up in my bathroom. You can do that with one handheld mirror and one big mirror, like most people have in their bathroom. I note that besides looking at plane mirrors, we will later look at curved mirrors and lenses, and you probably are looking at them in your lecture. I've got a document on Blackboard that you might want to check out that I labeled mirror notes, but it's really about mirrors and lenses, and it has a summary of useful qualitative results about mirrors and lenses. That's enough for now. I'll see you in the lab. Enjoy. Bye.